Hello everyone, welcome back to ECE410 Power Electronics, class number 6. In this class, I'm going to talk about two different options here. One is DC conversion without switching, so no switching over here. And this is with switching. Again, I'm going to divide this lecture in two videos. We're going to do the first one with no switching and second one with the switching. So let's talk about the no switching DC conversion. DC conversion, why is needed? If you look at everywhere, if you try to get a DC from AC, that goes through multiple conversion inside. Like for your laptop, you might need 12 volt. For your iPhone, you might need 3.3 volts, and other devices might need 5 volts. Everything coming from your wall outlet, which is 120 volts. So here they have AC to DC conversion and DC-DC conversion, and also control on that to make sure that your output voltage does not fluctuate when your input voltage fluctuate or changing the load. That's the main goal here. So your output voltage from DC conversion should be constant, even the input voltage is changing or load is changing or your temperature is changing. So those are the main factor to keep in mind. So first one, if you learn about this in even way back in ECE100, that voltage divider. So why we need DC converter when you can use just voltage divider to convert one DC level to another DC level. So voltage divider work like this, you know that V out is right here. So this is basically, I'm calling this is R2 and this is R1 here. This is the equation you have seen before. So for this, you need the V out is always smaller than V in. V out cannot be greater than V in. That's one limitation here. Another limitation is that look at the change in V out with respect to change in V in. If you see that that depends on your value of resistance. If your resistance value is changing, that also changes your output voltage. Right? For example, when you have a load here, load coming here with a R, let's say load, that means this is not R2 anymore. It becomes a combination of R2 and R load. So this is basically parallel of R load, right? So that equation does not work anymore. Voltage changes, and so that's why it direct change over here. There is no other factors. Changing voltage, the actual voltage is direct. There's no other factors in there. They're equal to each other. And also temperature over here. Your temperature change the resistance value. If that happens, their output voltage also change. So this one has direct impact of input voltage, which is your change output, and also load change can change the output, and temperature can change your output. So this is not a good design by any means to use when you need a constant output voltage. And for this kind of design, if you look at that, if you have a, let's say your RMS coming in 120 volts AC, your output is only 1 volt DC. If it's 10% changes happen, so let's how much changing? 10% change in 1 volt DC is 1 volt is 1 point. Out of this over here, 1.10, 10% minus 0.9 over 1. That's the change will feel in the output. So that means you have a 20% change at the output voltage, even though your input only changing plus minus 10%. So that is the change you could feel in the output if you don't have the control on the output voltage. So there are other things, line regulation over here, that depends on your input voltage. If input changing output, that's called line regulation. Load regulation is here. If your load changes, your current changes. If your current changes, your voltage drop changes. That also changes your and the voltage at the output. That's called load regulation. And temperature, as I said, temperature can change your resistance value. And also time regulation. How long it takes for your converter to get to the value you need. So that is drift, warm up value. That's also need to be considered. So these are line regulation, load regulation, temperature regulation, and time regulation are very important for any converter like quality. So now let's examine a very simple one here. This is a Zener diode. You all know that Zener diode can hold the voltage called Zener voltage VZ in reverse bias. In forward bias, Zener diode is a regular diode. In reverse bias, it can hold the voltage VZ. So let's say we have VZ is 5 volts here. So VZ is 5 volts. That means this diode will hold 5 volts across it. I'm going to get 5 volts over here, right? And to do that, we need a little bit of current going through the Zener diode. So look at that. Even if you don't have any load connection here, there's no load connection. This current is not zero. So it's non-zero. That means this current is coming from here. So let's say this is your source current should be equal to IZ at no load, right? That means even you're not connected load, you're losing some of the power right here with the source resistance. So that's one of the drawback for this shunt regulator, that in low load, no load, you're also losing power. So that one drawback. Another drawback is that when you connect load here, let's say you connect a load here, right? So let's say that this load current over here, very small current, let's say 0.2 amp, IL load current, and IG, let's say this is 0.1 amp. That means your IS now, IG plus IL, that would be 0.3 amps, right? So now let's say you're supplying 5 volts with 12 volts in. So V out is 5 volts, V in is 12 volts here, right? Let's see what is the efficiency of this one. So now with that calculation, as I said, it's 0.2 amp load, 12 volts to 5 volts here, and IG is 0.1, as I said. So now if you try it, the current flows through the drop of 7 volts, right? So RS needs to be this here. So that means why is that? So you want 5 volts out of 12 volts, so your 7 volts to be dropped across that source resistance RS, right? So to make that happen, you need to make sure that your 7 volts drop across the resistors RS when there is 0.3 amps going through it, right? So 7 over 0.3, let's do the math here. 7 over 0.3 is 23 ohms. 0.3 is 23 ohms when it's fully loaded. So it's RS is 23.33 ohm when it's fully loaded. When it's not loaded, no load, so no load, your IS is only 0.1 amps, right? So then your RS would be 7 volts. Still need 7 volts drop there, 0.1. So it would be 70 ohms. So can you see that what is the variation of it, right? You can go from between 23 to 33 ohms to 70 ohms. That's the range for the RS here. So you have to be careful how you select your RS. For this particular design, you're trying to keep it less than 75. That means you're saying that we're going to only use this 0.2 amps over there. So if we use 0.2 amps, your 7 volts, 0.2 RS, so RS is 70, so it's 35 ohms. That's what we're gonna shoot for. So we're gonna only calculate the load current, not with the IG. Let's say IG is 0 for our ideal calculation. Okay. So now in real calculation, if your IG is 0.1, then your power input power is V in, I in, right? I in is IS, that is 12 volts, 0.3 amps, that will give you 3.6 watt, right? And P out would be V out, which is 5 volts, and I out, which is load, which is 0.2. So 5 volts times 0.2 amps, right, will give you 1 watt, right? So this is the output, this is input. What is the efficiency now? The efficiency is P out over P in, right? That would be 1 watt over 3.6 watt, and that will get you 27.77%, right? So that's if it's not very good efficiency. So you can see that if your voltage change is greater than like you have a low output than high input, you have a lower efficiency for this kind of design. But this doesn't work. This design is many circuit board uses this because for a small power, like you're handling 1 watt or 2 watt power, you use this very cheap, and it works. Not efficient, but it works. Another one is line regulator or series regulator. Is that linear regulator or series regulator when you use a simple BJT to do it. Let me show you how it works. So this is a BJT, right? Bipolar junction transistor. And over here is base, right? And collector, emitter, right? So as you know that this current is IE or IN, this is our IC or collector current, this IB. For a good transistor, IB should be 0, right? If that happens, then your IE would be equal to IC, right? That means I in is equal to what? I out, right? Then let's say normally this drop over here is 0.7 volts for a BJT. Then if you have, let's say you need 6 volts out here, you want a 6 volts output, and B in could be higher than that. So that let's say that this is here your 6.7 volts. So 6.7 volts over here, 6.7 drop here, you get 6 volts. So their voltage is controlled by your control voltage over here. So if you want 7 volts, you need 7.7 volts. If you want 5 volts, you need 5.5 volts at this point. So that means your output, so P out over here, I out, B out, right? And P in, input power, is I in and B in. So then your efficiency, let's go back here. So efficiency is P out over P in, right? And so is V out, I out, V in, I in. And you know that I in and V in, they're equal to each other, so they cancel each other. So that here V out over V in. So efficiency depends on input voltage and output voltage, right? So think about that. If your output voltage is smaller than input voltage, your efficiency is directly affected, right? For example, if you have 5 and 20, you get efficiency of 1/4, which is 25%. So let's this is the one showing that how do you get the control voltage. The control voltage can come from your Zener voltage, as you saw before. Zener diode can hold their voltage constant, so you can use that Zener diode to give you control volt for the base of the BJT. So now, so no matter what you're dropping this, and also your voltage efficiency, your input output efficiency depends on 2 voltage levels, as I derived here, like here. So what is the effect of that? Let me go into one particular example here. If you're looking for V out is 12 volts and B in is 14 volts, you will see that your efficiency is 12 by, so your efficiency is 12 over 14 times 100% here, right? So that is a high efficiency. You can calculate that. I think that is around 85, if I'm not mistaken. It's 86. So this is 86%, right? So that's very good. But if we have this much difference in voltage, so your efficiency over here is 5 volts over 48 volts, and that is only 17%. So look at that. So your efficiency depends on your voltage level. That's also not a good design. Your efficiency should not depend on voltage level. So all three things we looked out there that both works as a voltage DC voltage conversion, but efficiency level depends on the voltage you're getting the output in terms in respect to input, and also the voltage divider depends on your load, and there is some also power losses for all of them. So our goal is to have a DC conversion that's a higher efficiency, at least 90% or higher, that is very independent of voltage output and input. All right. So to do that, we need to go into the switching. That will be the next video. We're gonna get that. And also here, your output voltage for this one can be controlled by this one here. All right. So and one thing I think I made a mistake over here. Let me go back and correct it. is that when I note them, over here, this is actually collector, this is emitter, and this is base. So I think I note them differently here. It should be IC, should be IE. All right, sorry about that. All right, with that, we're gonna end here. Let's go to the next video with switching converter.